It's kind of worse than I took
Sorry about that, the board was a mess. So it took me a while to clean it up. The trigger just broke. It's been 6 years. Broken. Another one. Okay, so as usual, I know this is the extra hour. No one complained about using this hour for lecture and the next hour for the extra hour. I think it makes a lot of sense to do it this way. If someone has some major issue with it, tell me, but again, it just makes a lot more sense to do it this way. That way I can give you tips. Again, 2 questions, 8 through 10, I believe, are going to be based on today's lecture. And then we're clear on Monday. And I try to finish the homework stuff by Friday. With the idea that you can start on it on the weekend. I'll set that up plenty of times, but hopefully not too much. So, also, I appreciate, we'll have the 10-minute break. I'll film those videos. Again, I need to recharge if you guys can just watch after it. So I'm just going to go take a 10-minute break. For the extra hour, I do have about 3 pages of notes. That means we'll end a little early. It's just changing the curriculum. We're actually going into a subject that's really easy. We're going to start thermo today. And it's relatively easy starting out. It's a little harder at the beginning, but it's relatively easy. So I just don't have a heck of a lot for the extra hour. So if you have questions, as I emailed you, I should have emailed you last night, it would be much better if you had questions for me on homework, or better yet, you now hopefully have seen the answer key and you're like, well, I don't get that. You know, I missed it, I don't get it, I don't understand the answer key. Ask me about that. I'll throw you a piece of candy. But as I emailed you, I miss a lot. My eyes are really getting bad, and I don't want glasses. So I really hurt people sometimes. And that, Reese's Pieces, guess what? They've been in the freezer all day long. Oh, and you know that's tasty, but you also know they're hard as rocks. So, you guys, you did great on sound yesterday. To me, yesterday was Wednesday. You did great on the sounds. Keep it up. That was awesome. So I do appreciate that quite a bit. So your neighbors who really want to hear what the heck is going on so that they can go on the test. So anyway, all right, so I know I'm rambling and we're already late. We got a lot to go over. Okay, now remember, always we go over what we did last time. Van der Waals equation, perfect gases, and how do you measure to what degree is your gas not perfect? And we talked about compression factors. And I'm perfectly capable of on the test saying, Tell me what a compression factor is. That's a reasonable question on a test. And here's one way to define it. And this is the way I like to look at this in terms of thinking it as a correction for PD equals nRT. It doesn't quite work, so we just throw in something that makes it work. It's temperature dependent. The way we did the Van der Waals equation was to figure out how to put Vm on the side. It wasn't perfect. And then we divided it by the perfect gas volume. And so this way, sorry, that's ugly. This way, it's the volume of the real gas divided by the volume of the perfect gas had that gas been perfect. Now, it's also equivalent, as I said yesterday, and I won't write it up to confuse you. It's the same thing as saying it's the pressure that you measure divided by the ideal pressure. That would be the same thing. Now, this is a bit of a nuance, and I don't want to kind of blow your head off and get your head running around like a hamster in a little cage where they just run. So, the funny thing about this philosophically is that in all our perfect gas, Van der Waals, Variol, always pressure can be multiplied by volume. So it's a little bit hard to say. When it comes to compression factors, are you really saying that the pressure is the perfect gas pressure, but the volume is not? In which case, you want to put it in this form. Vm not. And remember, not means perfect gas. So the pressure was okay, but the volume wasn't. But pressure is always multiplied by volume in some way or form. So it's equivalent to say, well, the volume was the perfect gas volume, but the pressure was off. Those are totally the same thing. So which one is it? Well, it's both and neither. right? It's a bit of a shade of gray. So anyway, just to point that out. Now, we also did residual volume, the limit. This limit, remember, it comes from the fact that we are working with a real gas, not a perfect gas, and it's the volume minus, again, the perfect gas volume at a very low pressure. These are people back in the day, like 1890s, whatever, when they started figuring out all this stuff, and they started to be able to isolate gases, they started making these measurements. This was nice and fun, and you can learn about molecules volume as on the homework. I show you that. So we're back in the 1890s. Now we figured out how to isolate oxygen from nitrogen by freezing it out. So now I have pure gases. Now I can make measurements, and I've got a little bit better balloons than those cow heads that stare at you blankly with their dead souls. And so they were able to make these measurements. They empirically fit A and B. And like on your homework, you're going to see that if you think about it correctly, that B really does get you awfully close to the real size of the atom. It's not perfect, it's a little bit off, but I mean, they were awfully close, and that's pretty incredible to make these kinds of measurements. And, you know, it's a freaking balloon, but this balloon can tell you what the size of the atoms are of the gases that compose it. So I thought that was pretty neat. Okay, then we then we solved both of these with the van der Waals equation. We saw that A and B have these conflicting roles in all cases, and I'm not going to do that derivation again. I just want to remind you. And anyway, so also a big warning. I'm just going to go ahead and erase this as we actually start talking about stuff we're supposed to talk about. Warning. Definitely I have those questions, those types of derivations. I am definitely going to put one on the test. So that was a very important lecture last time. Watch the film if you don't quite remember it. I had them all up to date. And it may take me until Monday to get these up. This one does take a while. Too long. The 2 hours just makes it take longer for me to translate them and put them up. Okay, last bit. I've seen, normally I don't cover this because I don't think it's terribly interesting, but then I found out something. It's on the GRE. And then I was like, oh, I didn't cover it. So I'm covering this. Let's look back at, I'm going to draw what the van der Waals equation does in terms of, as you should recognize this as an isotherm because I've drawn P versus V, meaning P must be constant. And here, so this is an isotherm. And van der Waals equation, as you did on the last homework, it's really not bad when you compare it to the perfect gas. For that methane, when it was about to condensate, perfect gas pressure was 161 bar, something like that. And the real pressure, the van der Waals pressure was 49 bar, and the experimental was 45. You can't tell me that. It didn't do an infinitely better job. And van der Waals also does this part right at lower temperature. And I'm not going to write down that it's a lower temperature because you know how to recognize that. There's this one point where the curve is completely flat. So I am trying to draw that as best I can. And then, as you lower the temperature further, the van der Waals equation does something really, maybe out of PowerPoint some things, I don't know. Should be some curvature there. Now, van der Waals equation does something very strange. Again, I have to emphasize for reasons that you will see in a minute that this is calculated, not experimental, but they're pretty freaking close. Except that the van der Waals equation does something really funky. All right, I'm not screwing up the drawing. I'm not screwing it up. I did that one pretty well. Now that's awfully odd. For an equation that seems to do a shockingly good job with minor modification, dV equals nRT, is doing something very strange. Yeah, so what? I don't see anything weird. It's just a curve. It's a curve that if I lower the volume of the gas, the pressure goes down. Now I'm pretty sure when I compress a gas, the pressure goes up. There's no such thing as a gas that if I lower the volume, the pressure goes up. No gas does that, yet the van der Waals equation is saying it does at certain temperatures. That's awfully strange. And there's a good reason. It's cool. But anyway, I'm going to get to this part. Let's talk about this part first. Let's zoom in. Zoom. Okay. At this point, GM, and I think it will be kind of obvious. You should not get confused in your notes what's happening. Oh, it's got to be like that. I do try to be accurate. Okay. Now, mathematically, this is an inflection right here, where the slope is where it's just definitely flat, so I'll write that down, inflection. Don't worry, I'm not going to ask you that on the test. What is this point called? Well, it's inflection. No, we're not doing that. But you should know some things about inflection points. All right, and let me just start you out with this. Again, you should have covered inflections. I don't know, I wasn't in your math class. Your teacher should have gone over inflection points. So what's this part? Even if you're not sure, what really, come on. Zero. Right, it's 0. Now, that's all fine and good. Lots of things can have 0 derivatives. All right, here's an example of something that's not an inflection. Parabola. Upside down parabola. I think those have names, whatever. Anyway, those have single derivatives at their apex. They're 0, but they're not inflections. There's one more criteria for inflection. Anyone remember? Second derivative is 0. Squared, and of course the proper mathematical symbolism is this, for whatever reason. I do try to get it right, but I will screw that up a lot. And there you go. All right. Now remember that I did say this before. Sorry, I should have brought this up earlier. The critical point. Critical point. I will actually probably want you to remember that when we cover phase diagrams, not right now. But below the critical point, gases and liquids can be in the same room. So, and above the critical point, you can't have liquids anymore. And again, don't even worry about that right now. It's just, we're going to cover that phase diagram. Okay, but that's what it is. Now, here's the Davis thing. I am perfectly capable of getting the van der Waals. So this is van der Waals equation. You might want to write that down. And my wrist kind of hurt, so I'm not going to do it. Actually, no, you did do this one. You did this one as part of your homework. Oh, except you used the Berthelot equation. But it's really the same thing, right? The Berthelot equation and the van der Waals equation are pretty much the same thing. 2a over v1 to the power. I shouldn't really even need one of this. Such an easy thing to do. Okay, this one is, I hate double derivatives, but you really get a little cross-eyed. But it's not too bad. And hopefully you can kind of just see it. I'm not going to ask you to work it, but hopefully it's kind of obvious what's happening. The m to the 4th power, right? 3rd, 4th, minus 2, minus 3. Okay, so there you go. So what? Okay, one thing about the critical point. For a single component, when we cover phase diagrams, for a single component, meaning it's steam. It's steam in a box. That's what it is. Single component. It's just steam. The critical point is massively unique. There's only one temperature and pressure, and of course that also dictates the volume, because at that point, so we're going to have 1 mole, so fix that. That means I've got pressure and volume, but if I have 2, the third is fixed, right? So this is going to occur for a single material at a very, very specific temperature and volume. Or I could say pressure, but I won't for various reasons. Especially because, all right, again, this and this and this and this. I've got 2 variables and they're both very unique. That's again my point. Can't reiterate that enough. I've got 2 equations and 2 unknowns. Well, what should I do with 2 equations and 2 unknowns? System of equations. I can solve them, right? I'll solve for t. I can put t over here. Doesn't look good for b. I'd rather put t over here. It doesn't look too bad. And then I put that t in there. And then I only have b. And then I solve for b. Right? And I actually put this as the extra credit question on a homework once. Sorry, on a test. You have extra credit questions on the test. Not a lot, right? But I have a cheap date, but not an easy one. So if you have this, I'll put it down here. That should be negative. Sorry. You're right. Thank you. The sign should switch. Sorry, folks. I get so used to my own notes that I stop looking at them sometimes. So sorry about that. I will make mistakes because I'm used to PowerPoint.
Thank you for catching that. I haven't screwed up too often, but I will do it again. Okay, now I'm not going to call it VM anymore because it's unique, so I'm going to call it the critical volume. And since I have gotten rid of T and I have VM over here, it has to be in the form of A's and B's. Those are the only variables left. And again, I look them up on the table. Okay, so this is just what they are. I don't, if you want to have an exercise in algebra, go ahead and solve them. But, as much as there's a lot of math in this class, I don't want it turning into a pure math class sometimes. I will violate that sometimes, but I would rather that didn't happen. So I'm not going to solve for these. It's just an exercise in algebra. I don't really care for that too much. All right, now that I've got the volume and temperature, and I'll make moles one mole. That means I'm only left with one thing. I have pressure is equal to van der Waals equation. I have pressure equal to stuff, and that means that I can plug these guys in there, and I get a unique pressure, the critical pressure, 27B squared. And again, hopefully he figures me out well enough to know. Don't ever try to when you're studying for the first test, okay, the critical volume is 3B. Critical volume is 3B. Oh God, no. I do not care about these minor details. I am not going to ask that on the test. All right, anyway. So what? Okay, now I can define the critical point of a van der Waals gas where below it's a liquid. It can be a liquid. It can be a gas, but above it can't. Okay, well, fine, great, whatever. This leads to a concept, and this is what I found in a GRE test. This leads to reduced variables. Sorry, OCD. Reduced variables. I'll go to the next board in 1 second. And what you do is, here's the reduced pressure. What it is the real pressure divided by the critical pressure. And therefore, the pressure is the reduced pressure times the critical pressure in a 5th grade level of algebra. Okay? Obviously, the reduced volume is the real volume per mole divided by the critical volume. And remember that is per mole still. It's just the symbology. And the reduced temperature is, of course, the temperature divided by the critical temperature. Okay, I shouldn't need to go into this. So what? Here's about that. Okay, let's write the van der Waals equation, which I know starts with pressure. Okay, because I know the van der Waals equation has pressure equal, and I just wrote pressure. I know it has the gas constant times temperature. See, I have not altered the equation. I know it has the volume per mole. Volume per mole. And it divides, you subtract out A divided by the volume per mole squared. See, that's why I like writing. I can kind of just tell you what's in the, anyway. Okay. Now plug in, what's I writing? So now, see, you have BC and TC. And PC. We have them. Right, they're right. Where are they? Oh yeah, right there. All right, so you can plug these in. P, C, T, C, BC from above. And what you get is, okay, so I have the reduced pressure still, but PC's been dealt with in such a way that once all the algebra is done, you're left with this. Everything is in reduced units. Of course, it should be squared no matter what. Okay, so there you go. And now you're thinking, so what? So what? What's missing? A and B. There's no A and B. Without A and B, how different are all gases? Perfect gas equation, right? If A and B are 0, you have the perfect gas equations. So if you don't have A and B, how different are all the gases? Okay, this is what I have to do to pull, because what I heard was, it's funny because, you know, like when waves mix, you hear those beating sounds? Anyway, so yeah, they're not different. Without A and B, you have the perfect gas equation. All gases are the same. There's nothing unique to identify a gas in the perfect gas equation. Now what that means is that when we plot for any gas, pressure versus an isotherm, a reduced isotherm, this is the behavior you get. Oh, sorry, sorry about this. Again, these are, what are the units? Unitless, right. See? Pressure over pressure. Unitless, so just 1, 1. Now that means that then at TC, I will get this behavior. And here's the inflection of the critical point. Okay, I'm sorry I wrote that so small. And that greater than TC, of course you see this behavior. And at less than TC, oh God, sorry. You get the funky behavior that I'm about to talk about right now. Okay, that's very exaggerated, by the way. If you actually do this calculation with the van der Waals, it's kind of hard to see it a little bit, but I just want to get the point across that this van der Waals equation does predict, it's just I'm exaggerating it so that it's easier to see. So anyway, so here's the neat thing with, and again, I did see it in the GRE, that all gases become the same if you use reduced variables. And sometimes, especially engineering, sometimes you use, I don't think you do this such anymore, maybe I actually prefer it when you guys would tell me, but because all gases become the same if you use reduced units, I used to find engineering tables where they put everything in reduced units so that it was easier, right? So if you're dealing with gas mixtures, or you have to make a decision kind of quickly in a process, you can look at a reduced unit table and know very quickly what to expect in terms of how your gas is actually going to behave in like a reactor or something. So anyway, that's just, again, it is what it is. I can see probably why I was never always super interested in it because, I don't know, it's just kind of more of a mathematical exercise. It's cool that that happens, and it's cool that the A's and B's, they just kind of happen to get wiped out. And it just means that all gases behave the same. Again, I always felt like it was more of an exercise in mathematics with this kind of lucky result being this right here. And I don't care too much about that. Here's something I do care about. This I care a lot about because this is really freaking cool. Okay, let me, all right, I'm going to switch subjects here. Let me do, okay, I have to think about how I'm going to graph this. Okay, forget reduced units. I don't care about that so much anymore. Now, let's talk about this behavior. As I mentioned, this is actually quite fascinating. Again, volume, it's easier to think about compressions and expansions. I'll do both. You compress a gas, the pressure should increase. I compress the gas, the pressure decreases. No gas has ever been observed to do that, so why, in God's name, would the van der Waals equation predict it? An equation more accurate predicts something ridiculous. That sounds ridiculous. All right, one little thing to note is that when people back in the day, what they did was, to fix it, they drew a line, and there's certain mathematical stipulations to where you draw the line, and not even going to go over it, but, and then they would do this. Just erase the parts that they didn't like. So exactly. Yeah, I sound like a politician, don't I? So they would do that and say this is what it really looks like because they just really could not handle the fact that the van der Waals equation is predicting something that just could not be correct. This has a name, and don't even write it down. It's called a Maxwell. I'm just telling you, just to tell you, the Maxwell construct. And we'll never see that again. All right, forget it. But there it is. Okay, here's the cool bit. Let me draw a bunch of these. So Let me draw a bunch of these. I'll get a little bit bigger here. Looks like my pen's almost dead. Hopefully I've got two backups. All right, I'll start at the critical temperature. And now I'll draw a couple of these inflections. Not a very strong one. As you lower the temperature, these weird inflections get more pronounced. They get kind of like lighter. And then you start to notice a pattern. Here, I'll draw a line. Obviously, we start here at the critical point. There's no Maxwell construct necessary for the critical point, but below that there is. And if I kind of draw this line that connects the endpoints of these Maxwell constructs, I get something kind of like this. There's a shape to it. I don't know, it is what it is, but there's this kind of obvious trims. It gets wider, and it defines like its own region. Okay, now again, this gas equation is predicting non-gas-like behavior, which everyone was flummoxed on, until someone did something blindingly easy. Okay, I've got a box of steam. And steam's critical point is pretty high, so I can lower it below the critical point and still have steam. And then I adjust the pressure or volume, or both. It's the same thing, right? They go hand in hand. Until I was somewhere in this region. I was there. I then looked into the box. What did I see? You already know the answer, don't you? This is the liquid state. See, the gas equation failed because there's not a gas, right? Why would the gas equation liquid? Why would a gas equation work in the liquid state? But here's the damnedest thing, and I can't get over this. The gas equation, because it included specifically A is in charge here, because it included molecular attraction, which is why gases turn to liquids, it predicted liquid behavior by misbehaving. Kind of like Firefly. So, anyway, I'm fascinated with that. I just think that's one of the coolest things in the world. The van der Waals equation is really, wherever it is, it's a very slight twist. Let's just shave off a little volume. Let's just shave off a tiny little bit of pressure. And damned if it doesn't predict the formation of liquids. It does not predict the formation of solids, however. I tried to see if it could do that, and it doesn't. So anyway, but, well, hell, I still think, I guess it was still worth the Nobel Prize. So, anyway, all right, now I'm hoping that you haven't been horrifically bored to tears with PD equals nRT, because that's done now. And again, I very well could ask a question on the test about, yeah, count on it. I'm so fascinated with this, even though I didn't spend a lot of time on it. That will almost inevitably make it to the test somehow. Reduced volume, reduced units, I'm not so interested in. It's kind of neat. I put it on the test once, but I'm not feeling it right now. Now I reserve the right to put it on if I do feel like it, but I usually don't. The residual volume, the compression factors, 100% likelihood, and likely a derivational question. Okay, so normally, see, I've been asked to make a major change to the curriculum because I normally go into a very different subject. Any of you remember Maxwell equations? Sorry, Maxwell-Boltzmann? The velocity of a gas, it's like the probability of a gas having a certain velocity as a function of said velocity. I normally derive that now, but actually they decided, it's funny how school rules work. That is supposed to be taught in 346. And I jumped the gun and taught it in 342. And that's fine if I teach 346, because then I just don't cover it, because I already did. But I don't know yet. You decide in March who teaches 346, and it's not bloody likely me. So that person may end up reteaching it, which is a waste of your time. Now you can cover something else that makes you smarter in an interview and gives you a better chance of getting that job that you want. All right? We don't want to waste your time. Repetition sometimes isn't such a bad thing, but not now. So I'm going to hold off on 340. That's going to be put in 346. It's a very difficult subject. The equations span the board, and I like doing it to scare the hell out of you when you're just starting, because life is sometimes full of equations that stretch across boards. You can't avoid that. But we reduce it down to actually a very simple equation. And I like doing that, but again, I've been told you got to stop. And by the way, again, it's because one of the things about how this school actually works, because it's like never clear. I only learned this stuff when I got the job, when I'm running the school. Now I understand the rules. Remember how I said 3 hours of credit means you have 3 hours of tests aside from the final? If a subject appears in the official course catalog, which Maxwell Boltzmann is in 346, if I violate that, oh man, I could get in so much trouble. So they told me, like, look, we got to knock it off. So because I could get in so much trouble. What I want to cover about the Maxwell Boltzmann, and I'm just doing this off the cuff because I'm not going to be looking at my notes here, obviously, is that the average value of something is equal to the integral of the distribution function. And by the way, you don't have to write this down. Here, I'll do 0 to infinity. I just want to point out something that a lot of you don't know mathematically is you're used to averages being add 10 numbers and divide by 10. That's not actually necessarily true. That is not necessarily going to give you a correct average. I know you've been taught that. That's something you probably learned in elementary school. What is elementary school? Of course you learned that in elementary school. You probably learned it in kindergarten. It's not necessarily true. See, that works, and again, actually, don't write this down. So this is a probability function. It's actually called a probability density. And again, you'll learn why in 346. But the way it works is that when you take, so this is whatever. This is coin tosses. This is black marble, red marble, green marble, put hand in bag, and what do you pull out? Now, if probability distributions are bell-shaped, like your grades, or if they're like top hat, like marbles in a bag, that's a top hat like of probability, then you can take your 10 numbers and divide by 10 and probably get an average. That is true. But nature doesn't always work that way. Most of the time, especially these bell-shaped things, nature definitely likes bell-shaped curves, but not always. The Maxwell-Boltzmann distribution of velocity, oh, it looks like a bell curve. No, it's not. It has a long tail. It's asymmetric. You cannot look inside of a balloon and take 10 gas velocities and divide by 10 and get the average velocity. You will get the wrong number. You will only get the right number actually if you count up every single one, which is not even really what you want to do to begin with. The way to do this, the actual correct definition of an average value is exactly this. It's the integral of the distribution of probabilities. And again, I know it looks bell-shaped, it's not. It's slanted. I hope you can see that. And you integrate it times the thing you want the average of, and there you go. So that's the real calculus. And again, and even in the next hour, I'm going to do a little bit of prep work. I'm sorry to you engineers, but I'm going to be prepping for 346 a lot in this class because it's pretty freaking hard. You can also do this. You get the average of the square. Because you know you actually cannot. You should all know at this point, maybe you don't quite remember this. If you take the average of the square value, it is not equal to the average value. In fact, it's greater. It's just oh yeah, I know that looks funky, but anyway, it's always greater. Okay, I'll just put it back this way. And so again, and that comes from this type of analysis. But that's true no matter what. And this is going to be again for 346. Now, the damnedest thing is that if I did all this, and this is why I was doing it, 1/2 average mass times average value squared, you end up with 3 halves RT. Okay, so that is, velocity is going to be obviously translational energy, that's kinetic energy. And it says that the average kinetic energy of a gas molecule, well, it's be like xenon, all right? The average kinetic energy of a gas phase molecule due to translational motion is 3 halves RT. That actually is proof of one of the most critical theorems of the most important theorem in thermodynamics. That's why I cover it. And I can't this time, but trust me, it's 5 days of algebra, so you're actually kind of better off. So anyway, this is what the Maxwell-Boltzmann distribution does. It says, All gas molecules have at the same temperature, have the same energy. That's another proof I'm not going to be able to do. And it says that their average kinetic energy due to pure translation is 3 RT. Okay, so what? Keep that in mind because I may get to it today, if not Monday. But let's start talking about thermo. Actual thermo, so maybe I'll get to it on this board. I may not. So thermo, switching subjects. And we start with heat and work. Work. I was going to my grad students, I see them in the hallway, and I look at them and say, work. But Anita, she said, but I am working. She has this little high Indian accent voice. But I am working. And then I look at her and say, we'll work faster. Anyway, keep work. And this is the beginning of thermo. And this is why they sound impressive to me. In fact, sometimes I was tempted, like on that NBC late night hit show Friends, to do the whole lecture in the German accent. And, anyway, new pit. So heat and work. Let's look at a molecule. Let's think about how a molecule sees this. Well, this might be my old backup pin. Okay, so we'll go back to a phenomenological model. That was my old backup pin. Let's see how long it lasts. Okay, a molecule hits a wall and bounces off it. Now, as far as it's concerned, it's been hit upside the head. Right? As far as I can tell, it got smashed. You know, the molecule may not feel like it's moving. You know, Einstein, everything's relative. You know, you can't actually legitimately say that the sun revolves around the Earth. It's just that the equations that describe that motion become highly complicated if you just do it the other way. So anyway, so this thing gets smacked over the head. Let's make it hot. Because, you know, the thing about thermo, I'll try to represent it this way. The thing about thermo is ultimately our entire planet is energized by burn. This is how we create energy for work. That's the lights. Technically, that's a form of work. And we do it by heating things. So that's why this stuff is so important. Now, you know, heat means that what I'm trying to represent here is that the wall is now hot, so you know that's kinetic energy. Heat is kinetic energy. It's shaking. So now the ball hits it. Now the ball hits it, but it gets smacked over the head harder, right? Because it was coming at it, and the wall was doing like this, and it was coming like that. So bam! It got really whacked over the side of the head. So I know I don't like to draw over stuff, but watch the video if you get confused by it. So it got hit harder. And it got some more energy as a result. Okay, that's heat versus, let's do work. Okay, here's the wall. That'll be nice and cool. Now work means that it's moving. Right? And I'm moving it. The molecule, before you started doing work, when the ball was stationary, it again bounced off it. But now, when it hit it again, when we were moving the wall, and that's a form of work, moving mass is work, requires work, that's always true. It got hit upside the head harder, and it gained some energy. From the molecules standpoint, can anyone tell me how are these different? Yeah, they're not. The molecule gets hit upside the head harder because the thing was kind of moving towards it when it hit, and it didn't particularly enjoy that, but whatever. So it's funny how I give round balls personality. But so these are kind of the same energetically to the molecule. They don't really care. So that's why when you talk about internal energy, U is internal energy. Wow, and thank God I had the foresight to have a second backup pin. You thought you were about to escape. Okay, internal energy, it equals and molecules energy. Looks worse. It takes a minute or two for this thing to get flowing. So anyway, that's it's one of these things. I never liked some of the platitudes I learned when I was taking this class. U is a molecule's energy, the energy a molecule has, and G is the total amount of energy available to a molecule. What the hell does any of that mean? Right? This one's actually relatively easy. If we're talking about xenon, I guess I can split the atom, I can split the nucleus of xenon and make a big boom, and that's energy. But we're not in nuclear bomb class now, so it may decay radioactively, and it will. Everything decays radioactively. That's actually the weak nuclear force. The strong nuclear force is how we build nuclear weapons. Gravity is not part of thermo either. Electromagnetism is, that's the last force, right? Electromagnetism, the electron cloud, remember, starts over at the electron clouds of the atoms in here. It creates that exchange energy, if you recall that lecture a while ago, and you don't have to know that. But that's why the thing bounced off each other. The electrons ran into electrons. Electrons make the round part of the atom, and of course these are made of atoms. They all have electrons. Electrons hit each other, and they bounced off. That's electricity. That's electromagnetism. So that's the one I care about. So when we talk about gases, and we're going to talk about helium, argon, xenon. Really, its energy is its kinetic energy, because again, we're not in nuclear class, not now. And so the only energy that I can really think about, because xenon can't rotate or anything like that. You can't actually, I'll go over this more, you can't pick up a xenon atom and roll it like a bowling ball. That's actually kind of nonsense, and I'll explain more of that later. So a xenon atom, the energy in terms of practical thermodynamics, the only thing I care about is how fast is this moving, right? Because that's really all I can do with it in terms of using compressed gas to power a car. Kind of a shitty way to do it, but that's one way you can actually drive your car down the street. You can actually do it with compressed gas. So that's energy, right? And the only energy that allows those kind of funky cars that people have, occasionally you'll see one like at an auto show. The only energy that allows it to do that is its kinetic energy. So I measure the speed of a xenon atom. I do 1/2 mv squared. That's its internal energy. That's all the energy it has, practically in terms of what we care about thermodynamics. Now, if I'm powered, oh no. Okay, this is a surprise. This was my backup, not the other. Oops, sorry. It didn't look good because it hadn't started flowing yet. I wonder which one it is. Okay, now if I don't, yeah, here we go. It's now flowing. If I let the gas be, and again, I'm going to build one of these funky high pressure gas driven cars, not gas like ordinary gas, just like regular pressure, then something has to change, right? You can't change things, you can't do things without something changing, and of course everything requires energy. So the internal energy of this gas is going to have to change. And that's either going to happen because I heated it up, or, in my little car example, I let it do some work. Now notice what my whole blah, blah, blah was on last time was that these are basically equivalent, right? And that's why they each have an equal share. It's not like, don't write this down, do not write this down. It's not like I'm doing this. No, work is not half as important as heat or vice versa. No, that's not right. They contribute equally because the molecule just doesn't seem that different. Now, here's the thing. Now, hopefully you're getting used to this symbology, and I'm going to go over that a little bit more in the next hour. But I'm going to have to hold you a little bit longer. Sorry about that. I need to hold you to do this. And we'll still have a 10-minute break. I have to power the camera. So maybe we'll stay maybe just a few. I know you're going to need me for this, but give me just extra 5 minutes. The class really needs to be about now. Give me just extra 5 minutes. And that is Q plus dW. This is exact. I know, folks. Yeah, it's a little painful. We're always here 2 hours no matter what. exact and inexact partials. Okay, maybe my other pen is the right one. Let's see if this is the right one. Okay, exact versus inexact partials. What? Okay, now what that means is, and I'm going to explain it here, path independent. And these are path dependent. Okay, you probably think, okay, what does that mean? That's a very strange thing to say. So I'm going to give you some straight up regular mathematical examples in X, Y, and Z, because you're used to that still, and eventually you will not be used to it once we're done with you. Example. Exact. And I'm going to talk about the change in Z, and that's going to be some weird little function, x dy plus y dx. And again, a little bit of multivariable calculus, which is not very hard. Now, I'm going to integrate these suckers. Remember, what's the value of this change? It has units. It'll probably be energy, but what's the value? Give me a number. 1. No, you did that last time. 0. It's 0. It has to be integrated. Right, now it has a finite value. Okay, we're going to integrate that. Now that's going to make this dz, delta z. It'll be an exact differential. And then I'm going to have a path. And I have x dy plus y dx. Now this whole path thing, what the heck, oh god, sorry that's so small. The whole path thing, what the hell, path? What do you mean path? When I solve an exact integral, I integrate it, and then I apply the limits. Where is a path? When you get into higher mathematics, every integral becomes a path integral. It's not really bad at all. Let's look at two paths. Let me draw y and x on my graph. And we're going to go from 1 to 2, 1 to 2. Okay, I'm sorry my writing is so small today. I don't know what's with me. Okay, we're going to go from 1, 1 to 2, 2. That's the path. It's, I don't know, it's mouse in a maze. Okay, let's introduce the concept of integrating along a path. This is leg 1, and this is leg 2. Now, we could have done it a more sensible way by going down leg 3. Okay. Now, what I'm going to do is I'm going to integrate down these different paths. Because, it doesn't make sense. What am I saying? Yeah, let's just do leg 1. And I see that x is constant. So y goes from 1 to y goes to 2. X to y plus y dx. Okay, problem? What's the change in x? 0. Okay, this is gone. That's not part of it. So now I've got the integral from 1 to 2 of x dy. What is with me? Sorry, I don't know why my handwriting is just not happening. Okay, that's going to be x is held constant. So I've got the integral of dy. Dy. And now notice that x is 1. And then my exact integral is this. 1. Right? Okay. Very simple math again. First day of calculus. Now let's do the second leg. And then I will in there because I know I'm going way over time. So we'll do the inexact example next time. Sorry about that. I really didn't spend much time. Okay, y dx plus x dy. Now at this point, sorry, I flipped it. Anyway, this guy is 0 because y is now constant. And now I've got, sorry. So I've got 1 to 2 of y dx. And okay, y comes out, and y is 2. and then x goes from 2 minus 1, and that's 2. Okay, now integrals, remember, are areas of the curves. So I have to evaluate the whole integral down this path. I have 2 paths. All right, I broke up the path into 2, but it's all one integral. So now how do I put these 2 together to get the total integral? Given that they're just areas under curves.
Adam.
Okay, just add them, right? If you want to know the area of a square, take the left area and add it to the right area. Of course they add. Areas are additive. So the total is 3. Okay, now let's do the third leg. Again, I'm sorry, I really kind of mismanaged time. Now here's the trick. Write this down. This really confuses people, right? Notice that it's a straight line with a slope. X is always equal to y. That means that I can come up here. I can come up here and make that x a y and that x a y. And we're going from 1 to 2. You know, I've got y dy plus y dy. 2y dy. Now again, you're perfectly capable of solving this. Me too, but I'm going to check my notes anyway because I'm always freaked out. Okay, that's going to be y squared, 1 to 2. All right, that's 4 minus 1, that's 3. Sorry again, my bad musical board. It's the same. Okay, so that's the point. Now you've seen a little bit about what it means to integrate around a path, which is actually, I know it sounds like complicated because there was never a path when you learned integrals, definite integrals. But you see, it's not really that bad. And when you're working with most functions, the integrals are path independent, as I've done right here. But now let me leave you off with this before we'll do our extra hour. And if you have questions, I have to tell up the camera and after a bit of candy. Z is equal to x dy is inexact. So next time on Monday, I will do the same thing, but I don't get the same answer, depending on the path taken. They will result in different answers. That's the point. So anyway, but I am way out of line on time. 10-minute break, and here, let me charge up the camera. And I don't have that much for the extra hour anyway, so smoke them if you got them.